Okay, so I'm going to go through some examples where you're solving linear equations. So the first one I want to show you is a solution that just works out a regular equation where you can find an answer to x. This is a simple example, I know, but just to get us warmed up. If we had this equation, x plus 3 equals 5, we can kind of see the answer is 2. There's just one answer to that, one and only one solution. X has to be 2 for that to be true, right? So the way we would solve it, though, if we looked at the steps, we would minus 3 from both sides, or throw the 3 across the line, and have 5 minus 3 gives us our one solution, x equals 2. But there's some special cases of this situation where you don't get just one solution. There's two special cases. One is where just everything works. Say we had the equation x plus 2 equals x plus 1 plus 1. Those two sides are basically just the same. This side could be simplified to say the same thing. X plus 1 plus 1 is x plus 2. Now, you might look at that and say, well, yeah, those are always going to be equal. Anything I plug in for x is going to work. If x is 3, 3 plus 2 would equal 3 plus 2. So x equals 3 makes that a true equation. But x could really be anything. X could be 5. 5 plus 2 will equal 5 plus 2, right? 7 equals 7. Anything you plug in for x. 1 plus 2 equals 1 plus 2. So x could equal 1. We tried 2, 3, any number you can plug in. So x will be all real numbers, or any real number would work. If we continue with our routine, though, of how we solve it, maybe we would subtract x from both sides to get those to cancel. And then you'd have just a true statement, 2 equals 2. So anytime algebraically, if you're going through the steps, if your variables drop out, your variables cancel each other out, there's no x left, just a statement. It's either a true statement or a false statement. When it's a true statement, then we say it was all real numbers. If it's a false statement, then it's going to be a no solution. So in this case, x could equal any and all real numbers. Sometimes they just use a capital R to represent that situation. Okay, let's do one where it's no solution. Let's say I wrote x plus 3 equals x plus 4. You may just think about that and say, hey, nothing's going to work here. Nothing's working out for x. There's no number I can plug in for x that when you add 3 to it, you get the same result as adding 4 to it. So there's no solution there. But if you go through your routine of minusing x from both sides, doing the same thing to each side, you see the variables do drop out, and you're left with just this false statement. 3 equals 4, meaning that's not true. That's a false statement. A false statement means nothing's working for x here. There's just no solution. Some other examples from your homework that I've picked out to kind of show this as well. I was going to do one where it works out to be a real solution, just a one solution equation here. So to solve this one, we need to get our variables on the same side. So you've got a 9t on the left and a 7t on the right. We can bring the 7t over to the left side to collect our t's. To get the 7t off of that side, we'd minus 7t. Do the same thing to this side, minus 7t. Or you may have been in the habit of, I do this sometimes in my explanation, just throw that term across the line. That's kind of the shortcut. If something's positive on this side, when you throw it across the line, it becomes negative. So 9t and minus 7t gives us 2t's on the left side. Then we've got the minus 9 still there and the minus 5. Then we continue to solve. We need the negative 9 to collect to the other side, get the constants on the right side. So the minus 9, when it moves over, I'm just going to use my shortcut and say it becomes plus 9. Giving me 2t on the left side. That's moved over. Negative 5 and plus 9 is 4. So now we've simplified it to 2t equals 4. The last step is divide by what's with your variable. So divide both sides by 2. The 2's cancel, leaving t, or that would be 1t, or regular t, equals 4 divided by 2. We simplified it to 2. So that's a one solution answer. When we're solving these linear equations that we do in this class, where the variable is understood to be the first power, so those are called linear equations, we expect to either get one answer, and that answer can be checked by plugging it in for the t's and make sure it makes both sides equivalent. 9 times 2 is 18, minus 9 is 9. Is that the same as 7 times 2, which is 14, minus 5? And that side's also 9. So we see it works out to make the two sides equivalent. It checks back in. So we either get the one solution, that's kind of the typical solution that we get, but there's these special cases that can arise where you get no solution, where it's just a bad equation where nothing would work, or you get all real numbers. It's a good equation, I guess you could say, where everything works. So I want to do an example of the special case with you. So on this next example, I can't really tell looking at it here. I guess if I really thought about it, maybe I could foresee, but it's not necessarily obvious that this is a special situation. So we can distribute the 2 and then bring down the minus 3. On this side, also distribute the 2, makes it 2x and minus 10. And then when we simplify on this left side, we got an 8 and a minus 3. Those would combine to be a positive 5. Just they're on the same side, so we're just using our combining rules or our addition rules to simplify that. Simplify each side as much as you can. And then when you get to this step is where you might realize something special's up with this, because you've got the 2x plus 5 and then the 2x minus 10. There's no way we can make that work out for us. And if we continue in our routine, we'll bring our x's, gather our x's to the same side, so this positive 2x moves over, becomes a minus 2x. So then you've got 2x's minus 2x's, so no x's. We don't write x at all, just the x is gone. The variables are dropped out. And what we're left with is a positive 5 equals negative 10, one of those false statements. And we say when you get this false statement, that means there was no solution. This just was a bad equation, a contradiction, you might call it. Okay, so that's that special case. Now let me do one of the other special case where everything works. Again, on this example, no special number here, just one I picked out of your homework set, that you can't really tell just by looking at it here that something special is going to go on. So we go through our steps of distributing 8x and 16. On the right side, distributing the 4 makes 8x plus 4, and there's a plus 12 to be brought down. So on the left side, I can't really do anything to simplify that any further, but on the right side, I've got a 4 and a 12 that's just asking to be combined, right? Those are like terms and sitting there beside one another, no reason not to simplify that. Then you can see, yeah, those two sides look identical. If you went through the rest of your steps and you brought the 8x over, the x's would cancel out. That's really when the special cases happen. It's when you lose your variables, when you're just moving along in your equation and the variables disappear or drop out on you. You're either left with a false or a true statement. If it's a true statement, that means anything would have worked in this problem. Any real number. X equals all real numbers. If you put in x is 1 to both of your sides, you'll see that makes the two sides equivalent. If you plug in x is 2, x is 3, 10, a million, a zillion, whatever number you can think of, you plug that in for both of these x's, and it just makes the two sides equivalent. So any real number, any and all real numbers would solve this equation. Hope that helps.